Welcome back to CS 111. Over the last couple lectures, we took a look at different algorithms for sorting data that we had. In this lecture, we're going to see how we can apply some of those sorting algorithms to lists. We'll take a look at, in particular, how we can go and implement sorted linked lists and sorted array-based lists. As we work with data in our programs, linked lists and array-based lists tend to be the most common way to go and organize that data. A lot of times we find that it's not enough just to keep track of the data, we also need to be able to go and sort it. Now, we can go and sort data that we already have stored in a list using some of the different algorithms that we've looked at in our previous lectures. Things like going and doing bubble sort or merge sort or whichever algorithm we want to go and apply. So one approach to going through and sorting data that we have in a list is to go and create a sort method that will just go and sort whatever's there in the list. The problem with this approach is that we don't necessarily know at a given point in time if the contents of our list are sorted or not. So every time I want to go and get something from the list, I've got to go and call that sort method to make sure that things are actually sorted as I expect. Alternatively, I could go through and call the sort method every time I go and add things. But that introduces a lot of extra overhead if we have to go through and sort that entire list every time we want to go and add or remove an item. A more common approach is to go through and design our list so that rather than adding an item and then sorting, we actually go and add the items in the correct location for where they should be sorted. So I'm saying basically that the sorting is built into the add method directly, not a separate method that we're going to go and call to go and sort the data after we've already gone and added that new item. We've already looked at one type of data structure this semester that allows us to retrieve items in a sorted manner, and that was the priority queue. Priority queues don't necessarily guarantee us how they're going to be storing values internally, but they do guarantee us that we'll go and be able to go and retrieve the items ordered by their priority, and that basically is however we want to define priority. We can use that to go and effectively sort our values. In the case of the example that we looked at with priority queues, we went through and actually stored things in a sorted order. And we went and sorted as part of the process of going and adding the new item to the priority queue. So you might wonder, with priority queues being available, why do we want to look at another way of going and sorting things? And I guess maybe a good analog to this question is, why do we need lists if we already have queues? Lists give us additional functionality that we don't have with a regular queue. We have the ability to go and retrieve any item from a list, whereas with the queue we can only go and retrieve the item from the front. And in fact, we actually have to go and remove that item. We have to go and dequeue it if we want to be able to get to other things inside of the queue. We kind of have the same thing with taking a look at sorted lists versus priority queues. With sorted lists, we have the ability to go and retrieve any item that's stored by its index. And we can also go and remove any item that we want by its index. We're not restricted to just going through and getting things at the front like we are with the priority queue. So it gives us more flexibility. So what's the difference between the functionality that we need to provide for a sorted list as compared to a regular list? What we'll see is that most of the methods that we're going to define in our interface for the list versus a sorted list, and then in our actual class implementations, they're going to be the same. But there are some key differences. When we go and work with a sorted list, as compared to a regular list, we're normally going to go and add a mechanism to remove by a particular item. Strictly speaking, we don't necessarily have to do this, but this is something that is relatively common in this sort of implementation, and we're going to go and support. So we'll go and provide a remove method that's going to go and take the item that we're looking to remove. There's also some stuff that we're going to delete that was in a regular list interface that we don't want to have in a sorted list interface. And these are basically things that might go and mess up our sorting. We're going to get rid of the version of add that takes two parameters where we can specify what index we want to store things at, because we don't want the user to be able to control where things are going to be added. We want to make sure that things are always going to be sorted. So we're going to rely on the one parameter version of add to go and add things in a sorted manner. For a similar reason, we're also going to get rid of the set method, where users can change the value that's stored at a particular index. We don't want users to be able to go through and potentially change something to a different value that would result in our list not being sorted, so set has to go. We're also going to have to go to our one parameter version of add, and in our actual class implementation, we're going to have to modify it because we want to make sure that it goes and inserts the new item into its properly sorted position in the list, not just at the rear of the list as our behavior was previously. For the other methods, we should be able to take what we had from the regular list and just port that over to our sorted list. The one case where there might be a difference would be if we were going and storing the data for our list using what's known as a heap. So a heap is another way that we can go and store data instead of doing it with linked nodes or with an array. Heaps can have some performance advantages in some cases, but the problem if we were to go through and use a heap, which we have not shown so far here, is that we would have to go and resort the data after we went and removed things. That's not going to be an issue with what we're doing. We can just go and follow our normal remove process, and we don't have to go and worry about resorting things like we would with a heap. Let's go ahead into Eclipse, and we'll see how we can go and take a regular list and make it sortable. Here in Eclipse, I've imported the starter code for this lecture. I'm going to go into the list interface project, and if we take a look here under our list ADT package, we've got the list interface that we went and coded up when we were going and working with regular lists previously. We want to use this as a starting point for a new interface for sorted lists. So what I'm going to do is I'm actually going to go and copy this interface. I'll right click on it and go to copy, and then I'm going to go into the same package, the one that ends in list ADT, and I'll right click again and go to paste. Here Eclipse is going to ask me for a new name for this copy of list interface. So I'm going to call this one sorted list interface. And then I'll go and open up that copy. So you can see here it went and renamed the interface itself in the code to go and match the new name that I specified. Let's go and clean up this code here a little bit so that it now goes and reflects being a sorted list. The first thing that comes to mind here is where I have the Java doc for the interface. So I'm going to indicate that this is now an interface for representing sorted lists. Next, I want to go and adjust the generic parameter here. I don't want to allow just any generic type T to be used with this interface. I need to make sure that it's something that is going to be sortable. Basically, it's going to have to go and implement the comparable interface, like we've done with a number of other things, including priority queues. What I'm going to do here is change inside the angle brackets where it just says T to say that T extends comparable, and then since comparable has its own generic, I'm going to go ahead and do question mark super T to say that this has to be T or something that T goes and inherits from because it's a superclass of that. I'll go ahead and make that change, and then we're going to have to go and adjust the methods here. We said that we want to get rid of the two parameter version of add, So I'm just going to highlight that and just remove it from the code. I'm also going to go and get rid of set. You might be wondering here why I went and copied list interface rather than just going and trying to extend list interface. And the reason why I'm doing that is that there's really no way for me to go and say that I don't want a method to go and flow down to the interface that is going to go and extend. I would still have a set method inside of sorted list interface if I went and extended the list interface. I couldn't get rid of it completely. The best that I could hope for would be that I might go and have that method, but for example, make it throw a not implemented exception. But that's really not a very clean solution. It's going to be confusing for users. So rather than having this try to go and extend our existing list interface, I actually just used that source code as our starting point and then modified it to get rid of the methods that we didn't want to have anymore. I want to go and tweak the Java doc for my add method. Right now, it goes and says that we're going to add the item at the rear of the list. And I want to update this to go and reflect that it's being added at its proper sorted location. So we'll say that we're going to add a new item at sorted location in list. Let's go ahead and add our new method now. So it's another version of remove, so I'm going to go and place it down by my other remove. Now this one is going to have two differences compared to the existing remove method. This one's going to go and return a Boolean value that we'll use to indicate whether or not the item was present when we went to go and remove it. It's still going to be called remove, but its parameter is going to be different. Instead of taking a primitive int for the index, I'm going to take the t-generic of an item. We'll be able to go and distinguish between these two methods by looking at the type of the argument that we go and pass. Primitives cannot be used with generics. So if I have a primitive int, it's going to have to be the case where we're taking a look at the version of remove that's expecting an index. If I get an integer class instance with the capital I, that's going to go through and fall here under the t-generic. So we'll be able to go through and make sure that we can differentiate between the two that way. Sometimes you'll see where people will go and design implementations so that there are slightly different names for remove methods if we're trying to remove by an index versus remove by the item. I might go and call one, remove item, maybe the other one remove element, or, remove by index. Something like that goes and distinguishes things. What I'm using here with calling things both remove is actually what Java uses in its own list implementations. And I'll go and provide some Java doc here. So we're going to remove the first occurrence of our specified item. The item is the thing that we're trying to remove, and we're going to return true if item was present and removed. So this is basically all that I needed to do with my interface to convert it from a setup for a regular list to one for going and working with sorted lists. Now that we have our sorted list interface completed, let's take a look at how we can use it with a linked list. So one thing that I want to mention as we get started here is the rear node field. So we've talked about with linked lists we can include a rear node field or not. And in the examples that we did, we went and included one. Even though we were going through and using singly linked lists, I still include the rear node field because it was convenient when we were going and just calling the one parameter version of add to go and add things on the rear of the list. If we're taking a look at things from a perspective of a sorted list, the calculus is not quite as clear cut as to whether or not you want to go and include that field. When we're going through and dealing with sorted lists, we don't have the add automatically going and putting things on the rear of our list. We don't get that benefit from it. It is useful in a couple cases if we're trying to go through and add a value that will go after the existing last node. If we go and code our program that way, we can go and see an advantage from it. If we're trying to go and remove the last node, we can get some advantage from it. Or if we're trying to go and access the value of the last node, we can get some advantage from it. Again, this really all boils down to how do we actually go and implement our methods for like get and remove and add in order to really see a benefit from this. So it's entirely possible that there can be zero benefit at all from going through and including the rear node field. If you were to go through and create a new sorted linked list from scratch, I might just go and forego it. You know, it's got some very specific cases that it does improve performance if you code things just right, but it results in more complicated code. In the case we're going to be looking at, we designed our class so that it already has that rear node field, and it's being used in some of the methods. It would take me work to go and strip it out of the class if I wanted to get rid of it. So even though there's not really a performance advantage per se to going and keeping it, I'm just going to leave it there rather than going and reworking my code to remove it. Here in Eclipse, I'm ready to go and start coding up the sorted linked list class. I'm going to right click on the singly linked list class, since it's going to serve as my starting point, and I'm going to go and tell it to copy. This package really isn't quite a great fit for my new sorted linked list class. So what I'm going to do is I'm going to create a new package. I'll right click on source here, go to new package, and I'm going to call this edu.wvu.cs111.sortedLinkedList. And I'll tell it to finish. And then I'm going to go and paste my file inside of this new package. So I'll right click on it and tell it to paste. You can see here that I've got this sorted linked list class here as well. And I want to rename it because I want to make sure that it has a descriptive name. So I'm going to right click on my class, go to refactor, and tell it to rename. And I'm going to say that the new name should be sorted linked list. I'll tell it to finish. And then I'll go ahead and open up that class. I'm going to update the Java doc to indicate that this is now an implementation of a sorted list. And I need to change the interface that we have listed here that we're implementing. Instead of doing list interface with the generic T, I want this to be sorted list interface with the generic T. I need to make sure that I go and import now the sorted list interface here. So I'll use the quick fix to go and import that. And then I'm going to have to go and make some additional changes. First one here is that I'm going to have to go and add the unimplemented methods from my new interface. The second one is that I'm going to have to change the T generic here. I'm going to have to do the same thing that I did back in sorted list interface and say that T needs to go and extend the comparable interface. So inside the angle brackets here for T, I'm going to say T extends comparable, and then we'll do for comparables generic question mark super T. Let's go ahead and clean up our implementation to get rid of the two methods that are not in sorted list interface. So I'll go to the 2-parameter version here of add, and I'm just going to highlight it and press the backspace key on my keyboard. I'll do the same thing with set. You can see that when I went and deleted those, I got rid of the errors that were showing here in Eclipse. Those errors were because I had the override annotation on those methods, which meant that those methods needed to go and override something. But because I had eliminated those methods in my sorted list interface, there was nothing there for them to go and override. So that one triggered the errors. I do still have a warning here, and that it's that the list interface is never used that I'm going and importing. So I'll go and delete that import there. We are instead using sorted list interface instead of just plain old list interface, so it wasn't needed anymore. For the sorted linked list, I'm going to have to completely rewrite what's inside of my add method. The existing implementation goes and adds things at the rear of the list, but I want to change that so it goes and adds new things at the appropriate location in the list so that the values of my list are sorted. What we're going to be doing here is essentially an insertion sort. For adding things, we're going to have a couple different scenarios that might play out. The first one that we're going to look at is the simplest one. That's where we have an empty list. So I don't have anything that I have to compare to. If we want to go and add a new thing here, I just go and create the node with my new value. I go and set the front node and rear node fields to go and point at that new node because it's both the front and the rear since it's the only thing there. And then I need to go and increment the size field to reflect that I now have one thing inside of my sorted list. Another situation that we can run into is where the item that we're going to add has a value such that it should become the new front of the list. So let's say that we have this list that's shown on screen right now where our front has a value of 10 and things are sorted in ascending order as we go along. I'm going to go and add a new node that's going to have the value 5. So let's see how this is going to work. I'm going to go and create my new node first, and I'm going to go and look at that value 5 and realize it needs to go before the existing front. So what I'm going to do with my new node is I'm going to set its next node to point at the current front node. That way I'll be able to get from 5 to the rest of the nodes that are in my chain. After I've done that, I can go and make my new node be the front node. So we'll start off with 5 now, and then we'll go through the rest of our chain with the 10, 20, 30. After I've done this and got all of my links set up right, I can go ahead and increment the size field to reflect that we now have another thing stored. Next, let's take a look at a case where we want to go and insert a value that will place our new node in between existing nodes that we have. So right now I've got 5, 10, 20, and 30 in my list, and I'm going to go and insert a new value of 15. The way this is going to work is I'm going to go and create a new node, and then I'll go ahead and create a current node variable to keep track of where I'm at in the list, because we're going to have to iterate to go and find the correct location. Initially, it's going to go and point at the front node of the list. I'm going to use a while loop to advance the current node pointer down the nodes in my chain until I find the node that will be immediately before the new one that I need to insert. What I'm going to do for my while loop is it's going to go and advance the position of current node while two things are true. The first thing is going to be while the value that's in my new node, so its data, is greater than or equal to what is in my current node's next node's data. The second thing that we're going to go and iterate for is if the current node's next node is not null. The reason why we go and have these two conditions, going through and checking for current node, next node not being null, that goes and helps us avoid null pointer exceptions. But it also means that we're going to go through and stop when we get to the last node in our list. The reason why I'm going through and comparing the value in my new node to the current node's next node has to do with the fact that we have singly linked list here, so we can only go forward. If I go and overshoot the location of where my new node is going to need to go, like say if current node advanced up to 20, I've got no way of going back to be able to update the next node field on the node that was back there before it. So what I always have to be doing is I have to be looking forward. I need to figure out, is this new node going to go between me and the node that currently comes after me? Because if so, then I'm going to have to go and update my next node field to go and point at that new node. So that's why our loop is going through and looking at to see if new node's data is greater than or equal to current node's next node's data, rather than just looking at current node itself. Once I've found the correct spot where current node will be the one that's immediately before where the new node's going to go, I'm going to go and set my new node's next node field to point at current node's next node. So here, current node is 10, the node after it is 20, and I'm inserting 15. So I'm going to make 15 go and point at 20. Then I want to finish going and hooking my new node into the chain. So I'm going to set my current node's next node to point at the new node. So now 10 will point at 15, 15 points at 20, and I can still get to the rest of my chain. To wrap things up, we'll go ahead and increment our size field so that we have an accurate count of how many things are there. The last case we're going to look at is where the new node that we're going to be adding will end up getting positioned after the existing rear node. Now, I could go and try to design things to take advantage of the rear node field and sort of short circuit the process by comparing the value that's in my existing rear node to the value that is in my new node. I'm not going to go and design that implementation though. The way I'm going to show you here is something that'll work pretty much whether or not we have that rear node field, and this way is also going to actually allow us to share just about all of the code between the case where we're adding between existing nodes and the case that we're looking at here where we're going and adding at the very rear. So for this here, if we're going to add at the very rear, we'll start off the same as if we're going to add between existing nodes. We're going to go and create our new node. And in this case, our new node is going to have a value of 40. So it's greater than all of the existing nodes. I'm going to go and create a current node variable and point it at my front node. So it's going to be pointed at 5. I'm going to use the same type of while loop to go and advance over my existing chain of nodes to find the node that will be immediately before the new one I'm going and adding. I'm going to go and loop and advance the current node position while my new node's data is greater than or equal to the current node's next node's data, and while current node's next node is not null. So in this case here, the value 40 is going to be greater than current node's next node when we're at 10 and when we're at 20. 40 is greater than 30, so we're still going to go and advance one more time. When we get to the point here where current node is pointing at the existing rear, our data is still greater than what's at 30, but I don't have a next node anymore. So I don't have the next node, so I can't even go and compare the value with that next node. What's basically going to happen here is that my new node is going to get tacked on to the end of my chain. So what I'll do is I'm going to go and actually set the current node's next node so that it goes and points at my new node. Next, I'm going to finish hooking my new node in by making it be the rear node. I'm going to update my list instances rear node field so that it goes and points at that new node we just added. And to finish tidying things up, I need to increment the value of my size field. And that'll wrap up adding our new node at the end of the list. Let's go head into Eclipse and we'll see how we can code things up for our updated add method. Here in the add method, I'm going to keep this first bit here where we go and create our new node, but everything else after that we're going to get rid of. So we're starting off right now where we go and have our new node created. We're then going to have to go and figure out where that new node is going to belong. And so as we saw, there's 4 different scenarios. It could be with 2 of them that the new node is going to become the front of our sorted list because either the list is empty or the new node has a value that's going to be lower than whatever's at the front right now. The other two cases are basically that it's going to go in between nodes, so someplace after the front, or that it's going to go after all the nodes and become the rear. So I'm going to use an if-else type setup here to figure out which of those two scenarios applies. We'll start off by trying to figure out if the new item should be the front node. So I'm going to do an if statement here, and the first condition's where we have an empty list. So we'll say if this dot is empty, or, so I've got bar for the logical or, I want to go and compare the item I'm trying to add to what's in the front node right now. And I want to do this in a method that is going to be aware of nulls, so that I don't get a null pointer exception. So I'm going to go and use the objects.compare method from java.util. So I'm going to do a set of parentheses here for this condition because it's going to be a little bit more complicated. I don't want to just kind of leave it floating out there inside the if. My comparison here is going to be saying if java.util.objects.compare, and I'm going to go and compare item as my first argument, and the second argument is going to be this.frontNode.getData. So basically I'm comparing the data value that's stored in our front node. And then I have to provide a comparator that is going to handle the nulls and will go and order things based off of the compare_to method in whatever class I'm dealing with. So for this here, I'm going to use the comparator java.util.comparator.nulls first. So if I have a null value, it's going to go first. And then inside the parentheses for nulls first, I have to say what to do if I don't have a null, if I have a non-null value, which is most of the time what I'm going to have. So I'm going to have it use the natural order comparator to go and fall back to using compare_to essentially. So we'll do java.util.comparator.naturalOrder. And I'm going to have 3 sets of closing parentheses, and then I'm going to go through and check to see if the result coming back from compare is less than 0. If it's less than 0, it means that item should come before frontNode.getData. So basically, we're going to go and have this be our new front node. Inside the if block, I'm going to go and update my new node's next node to point at whatever is at the front right now, if in fact there's anything. So I'll do new node.setNextNode, and I'm going to set it to this.frontNode. If there is an existing front node, it's going to become the next node after this new node. If there's nothing else in the list right now, I'm just going to be setting next node to null. So either way, I'm okay. And then I'm going to go through and make the new node be my new front node. So I'll say this.frontNode equals new node. Let's go ahead and code up an else block that'll take care of where the new item is going to go someplace after the existing front. Here we're going to have to go and loop to iterate to find the correct position for our new node. I'll create this var called current node, and I'm going to set it equal to the front node that I've got. And then I'm going to go and write a while loop. We're going to have 2 conditions that we need to go and check with our while loop. The first one is going to make sure that before we go and advance current node to the next node, that there is really a next node there, that it's not just null. So to go through and basically test here, current node.nextNode is not equal to null, what I'm going to do is actually take advantage of the isLastNode method that we created as part of the singly linked node class earlier in the semester. I'm going to write a test here that says I'm going to go and advance while current node is not the last node. So I'm getting the Boolean value back from isLastNode, and then I'm going in basically flipping it around with that exclamation point. So we'll advance to the next node if that is true that current node is not the last node, and if we determine that we need to go and advance more nodes to find the correct position. For this check, I need to go and get the data that's stored in current node's next node. I would have a potential null pointer exception come up if current node's next node is null. As it turns out, that's what isLastNode is checking. I want to make sure that I put my test here for isLastNode first, because the way if statements, when we have multiple conditions get evaluated, is it starts at the left. And if this goes and evaluates that this is in fact the last node, this test is going to go through and fail, and then it's not going to evaluate the rest. So I don't have to worry about that null pointer exception actually going and coming up. Since I could have a null value stored as the data inside of a node, I'm going to go and use the objects.compare method here for going through and comparing to figure out if I need to move further down my chain of nodes here. So this is going to look basically like what we did up with our earlier test. We're going to go through here and say that we're going to do java.util.objects.compare, and we're going to go and try to compare item against the data that's in our next node. So I'm going to do current node.getNextNode. So that's a method, and that will go and get me the next node. And then I want to call getData on that to go and get the actual value that's stored inside of my next node. And then I'll go and use my nulls first and natural order comparators. So we'll have java.util.comparator.nulls first, and then we'll pass that java.util.comparator.natural order to go and rely on the compare2 method in our object to go and actually do the comparison. Now here, the conditional test that I'm going to use is a little bit different than what I did previously. Before, I was going through and wanting this test to go and say true if the item should come before what's in the front node. Here, what I want this test to be true is if the item should come essentially after current node's next node. And for that, I'm actually going to go through and do greater than or equal to. So if they're the same, I'll go and put the new item right after. So notice that I've got opposite basically of what I had before. I've got greater than or equal to 0, because if item is greater, I need to go further down the line. Inside of here, I'm just going to go and iterate to the next node. So I'm going to say current node equals current node dot get next node. When we get out of the while loop, current node is going to be set to the node that will be immediately before where our new node is going to go. I need to go and make 2 updates to our next node fields here. The first thing that I want to do is go through and set the new node to point at the item that's after our current node. That way I don't lose access to the rest of my chain. So I'm going to say new node dot set next node, and I'm going to set it to current node's next node, which I'll get from calling the get next node method on current node. So that's going to make sure that my new node will point to everything that is going to end up coming after it. And then I want to go and update current node so that it goes and points at my new node. So I'm going to say current node dot set next node, and I'm going to set it to new node. So this will go through and take care of hooking up the chain starting from the front so that it has my new node on it. I do want to go and update the rear node field if the case is that my new item is the new rear of the list. So I'm going to do an if statement to check if I need to do that update. And I'll know that I need to do that update if my new node is the last node. And if that's true, then I'm going to go and set this.rear node equals my new node. So I'll have that rear node pointing at the very last item in the chain in case I want to do something with it. After I go and update the rear node field there, the last thing that I need to do inside the method is go and increment the number of items that are in my list. So we'll do this.size plus plus. The last thing that we need to do with our sorted linked list class is go and implement that other version of the remove method. Let's go down here to where we have the stub that Eclipse created for us when we told it to add unimplemented methods. And I want to go and just get rid of the existing code inside of the body here. For my implementation here, I'm actually going to rely on existing methods that we already have to do all the work. All I have to really do is just go and kind of get the data in the right format so that we can go and call the index of and the other version of remove for the two methods that we're going to be using. What we're going to do first here is we're going to use index of to try to locate the item that we want. So I'm going to say int item index equals, and I'm going to go and call this dot index of, and I'm going to go and pass it the item that I'm looking for. Now that I have this index value back, I want to take a look at it to see if it actually is a real index in the array, or if it's a -1, which signifies that the item could not be found. Because if the item couldn't be found, then there's really nothing else for us to do in this method. There's nothing for us to actually go and remove. And what we're going to do here is just go and return false, which, based off of the Java doc that we wrote, signifies that the item did not exist inside of our list. Assuming that we have some value other than -1, that means that we were able to locate the item. And so we're just going to go and take that index that we got, and we're going to go and feed it over to the other version of remove. I'm not interested in the return value from the other version of remove, because this is just going to return true or false. I don't need to know the actual item that we removed. So I'm going to say here this.remove, and this is going to be the version of removing by index, because I'm going to go and pass it a primitive int. So it's going to call the correct one based off of the type of the argument that I'm going and providing. So if I go and call the one here with item index, which is an int, if I look at the documentation, it's going to remove the item at the specified index from the list, because it's calling the version that takes a primitive int. Once we go and call the remove method, we can be sure that everything should have been removed here. If there was a problem, basically it would have been really just limited to us not finding the item, and we would have returned false. So if we've gotten to this point, everything should have been there. We should be able to go and say that we found the item and removed it. And so we'll go and return true. So that finishes up our sorted linked list implementation here. We've now got something that will go and sort values as we go and add them to the list, so that we can go and retrieve things and know that they'll be coming back to us in a sorted order always. Inside the starter code, under the default package in sorted linked list, there is a sorted linked list demo class that you can go and open up that we can use to test out to make sure that our new linked list actually goes and sorts values as we add things. We need to go into the main method here, and we need to go and change the types that are listed for where we go and create the numbers list. I'm going to go and change the actual type for the variable itself to be sorted list interface instead of list interface. And then for the class itself, this is going to become sorted linked list. I'll need to go and import this new class and this new interface. And then I can go and get rid of the unused imports now, since I'm not importing the old class in the old interface. But with that change in place, now these values should be getting automatically sorted into the proper location as we go and add them to the list. So let's see if this works. We're going to go ahead and run this code. And if we take a look at our results here, we can see that, in fact, everything is getting sorted, including cases where, like 65, we ended up with 2 of the same value being inserted into the list. So our sorted linked list here is working as intended. Now let's turn our attention to converting our existing array-based list into a sorted version. We'll head into Eclipse and take a look there. For our array-based implementation, just as we did with our linked implementation, we're going to copy the source code of our existing class to serve as a starting point for our new sorted class. I'm going to right-click here on the ArrayList.java file in Package Explorer and Eclipse, and I'm going to choose to copy that to the clipboard. I want to go and make a new package to contain my sorted implementation. So I'll right-click here on the source folder and go to New Package, and I'm going to call this package edu.wvu.cs111.sortedArrayList, and I'll click Finish to get that new package, and then I'm going to right-click on that and tell it to paste to go and create a copy of the ArrayList class. Now, I want my new class to be called Sorted ArrayList, not just plain ArrayList. So I'm going to right-click on this new file, and I'm going to go Refactor and Rename, and I'm going to change the name so that it reads Sorted ArrayList. And then when I click Finish, Eclipse is going to go through and update any of the references to that old ArrayList class that were in that file, or actually anything that was going in importing that class, and it's going to go through and change them to the new name. Let's go ahead and open up our file here. I'm just going to update the Java doc to say that this is an array-based implementation of a sorted list. And then I need to go down here where we're specifying the generic T for the type of items that I want to store inside the list, and I'm going to have to make sure that T goes and implements the comparable interface. So I need to change this to say T extends comparable, and then for the comparable generic I'll do !, super T, so that I have T or anything that is a superclass of T. I'm also going to go and say that this class implements sorted list interface, not just plain list interface. And I'll need to go and import that new interface up top. I need to make some changes to the methods inside of this class to go and conform to the new interface. I need to go and make sure that I have the new version of remove, for example. So if I go and hover over where it has sorted array list, I'm going to tell it that I want to go and add unimplemented methods. So that'll go and add the version of remove that takes the item I'm trying to remove. I'm going to go through the list of methods that we have here, and I'm going to prune the ones that we said we no longer needed with our sorted implementation. So we're going to have our version of add that takes 2 parameters because we don't want to allow the user to be able to specify where they want the item, because the sorting is going to figure out the correct location. So I'll get rid of this method. And you can see that the other version of add, the one that we're going to retain, was actually calling the version that we just removed. We're going to have to rewrite this method anyhow to handle the sorting, so we're going to leave this alone for the moment. We'll go down and get rid of our other method that we need to eliminate, and that one is the set method, so that we don't go changing values and potentially render things out of order. So I've got that in place, and then I'm going to go up to the top and I'm going to delete the line here where we're going and importing list interface, because we're no longer using that, so it's an unnecessary import. When we go and add new values with our array-based implementation, it's going to be a lot simpler than when we had our linked implementation. There, we had to figure out where the new item was going to go in relation to other items like the front, and we had sort of different processes that we had to go and follow depending on how things are going to be positioned. Working with the array-based implementation, we're more or less going to follow the same process no matter where the new item is going to end up, and that's because I have access to each of the items in my array directly. I don't have to worry about starting at the front node and then iterating through or potentially updating what the front node is. I can get to any element in the array the same as any of the others here. When we want to store new things in our array-based sorted list, we're going to start off by making sure that there's actually room for that new item. We're going to look to see if there are any empty elements in our array. If there are, we're fine and we can move on. If the array is completely full, we'll have to replace it with a larger array before continuing. Once we're sure that we have space to go and store the new item, we're going to start looping backwards. We're going to begin at the last element that actually has any data in it. So this index is going to be size -1. And what we're going to do is we're going to compare the value in this element to the value that we're trying to add. So for our example here, let's say that we're trying to add 7. I know that 7 is less than 20, so that means that 7 is going to have to appear someplace to the left of 20. I've got an array, so I can't just go and insert new nodes in place like I did with my linked implementation. I'm going to have to move the values that are currently occupying the location where my new one's going to go out of the way. So to make room for things, what I'm going to do is take the value that's in my current element, 20, I'm going to copy it to the location to the right of me, and then I'm going to go and move over to the left one spot. So temporarily here you can see that I actually have 2 20s stored. I'm going to repeat the same process again. I know that 7 is less than 10, so I'm going to have to go further to the left. I'm going to copy 10 to the right one element, and then I'll go and move over to the element to the left. Now here, I know that 7 is not less than 5. So I'm going to fall out of the loop. I'm not going to copy 5 over, and I'm not going to go and move my index I'm keeping track of to the left any. In this case here, we're also already at index 0, so I couldn't move anything to the left of it because there is nothing to the left of it. Once I fall out of the while loop, I'm ready to go and store my new item, and that's going to be placed in the element to the right of the one that I was looking at. So you can see that index 1 here is where I'm going and storing the value 7 because I'm currently got my arrow pointing at index 0. So we had made room for 7 here by shuffling the other things over to the right one spot, and we took advantage of that space that we made. Once we've stored the item, we just want to make sure that we go and increment the size field to reflect the current number of items that we have stored. Let's go ahead into Eclipse and see how we can code this up. Let's go ahead and update our add method so that we add things in a sorted manner. I'm going to get rid of the code that's currently inside of add because we're not going to reuse any of it. To start things off here, I'm going to make sure that we have enough room in our array. So I'm going to call this .expand data capacity, which will take care of creating a larger array if it's needed. Once I've done that, I'm going to start my looping process to figure out the correct location for inserting the new value. And I'm going to address here in my comment what we're doing. We're going to start at the right side of existing values and search backwards until we find location. So I'm going to create this int that I'm going to call current index, and I'm going to set it to this.size -1. So initially this is going to point at the last element I'm actually using to store values in. I'm going to have a while loop that will go and continue to iterate until we find where we need to go and insert things. Bear in mind as we go and do this loop here that we'll be inserting the item into current index plus 1 as the location. The first thing that I'm going to check in the while loop is to make sure that my current index is greater than or equal to 0. And the reason why I'm doing this here is that 0 is the very first element that I could have inside of my array. -1 is not going to be valid, so I'm not going to want to check to see if there's anything in index -1 because that's going to give me an index out of bounds exception. So my first test here is to make sure that current index is greater than or equal to 0, and then I'll have a logical AND with my second condition. And here I'm going to use objects.compare to figure out if the item that I'm trying to insert should be to the left of the location that current index is pointing at. So I'm going to say java.util.objects.compare. I'm going to tell it that I want to compare item to this.data sub current index, and then I'll use a null safe comparator. So for my comparator here, I'm going to do java.util.comparator.nulls first, and then I'll pass nulls first a natural order comparator. So I'll do java.util.comparator.natural order so that we go and rely on the compare to value for our objects that we're trying to work with. And we want to keep looping while the value is less than 0. So I'll have 3 closing parentheses, and then my less than 0, and then 2 more closing parentheses, and then I'll have a set of curly brackets. Inside the while loop, I'm going to do 2 things. The first is I'm going to go in and shift the existing item that's stored at current index to the right 1 element. So I'm going to say this.data sub current index plus 1, so this is the right 1 element part, is going to be equal to what is currently in this.data sub current index. Then I want to go and move my current location to the left 1 element, so I can go and repeat this whole looping process to check this new spot. So I'll do current index minus minus to decrement it. Because of this current index minus minus business, current index will end up being the index before where we're going to go and insert things. If the new item is supposed to go at the very front of our list, if it's supposed to go in index 0, what we'll actually run into is that coming out of this while loop, current index will be -1. And that will go and trip us to fall out of the while loop. Obviously, I can't go and install a value in the array in location -1. 0 is the lowest possible index. And we said that we want to go and put it to the right of whatever current index is anyhow. So when I go and place my new value in the array, I want to make sure that I go and correct for that final decrement of current index. So I'm going to say this.data sub current index plus 1, so that I'm sticking it to the element that's to the right of whatever current index would be pointing at, and I'm going to store item there. And then once I've done that, I just need to go and increment size to keep track of how many things I have. Let's go ahead and do our version of remove that takes the object we're trying to remove. And our implementation here is going to be identical to what we did with the linked list version of things. And the reason why is that we were just relying on the other methods to actually do all the real work for us. So the kind of the interface that I get from the other methods, that hasn't changed any. It's identical that what index of does for when I'm working with an array versus a linked list. Same goes for the version of remove that takes the index to remove. Those are the same. So I can actually go and write the same code that I did for the linked list here. We're going to start off by going and attempting to find the location of the item that we want. And I'll create this int called item index, and that's going to be equal to the return value from calling index of for the item. We'll check to make sure that the item was actually found, and if it's not found, we're going to return false, and we're going to know if it's not found if item index was -1. Assuming that we actually found the thing, we're going to go ahead and call the version of remove that takes the index. And for here, I'm going to call this.remove, and I'm going to pass it item index, which is a primitive int. So this will make sure that it goes and calls the version of remove that takes a primitive int, which is the one that works off the index. And then when we're all done here, if we've gotten to this point, it should be that the item was actually there, so we found it, and then now we've removed it. So we'll go ahead and return true. There's one more thing that we have to do to finish up our sorted array list class, and that's in our constructor. Right now, we're going and saying that we're going to take this new array of objects and we're going to go and cast it to our tGeneric. This is going to be a problem since we went and said that the tGeneric has to go and implement the comparable interface. I'm going to actually get an exception when I try to run this code and it tries to do this cast, because it doesn't necessarily know if object goes and implements the comparable interface. What I need to do here when I go and create my new array is I need to go and change it so that's not of objects but of comparable. I don't have to go and provide a generic parameter for comparable here. I just say comparable. But that will go and make sure that whatever items are stored inside of that array go and implement the comparable interface, and that'll get rid of the problems with me trying to cast things. With that in place, let's go and take a look at the demo class, sorted array list demo, and go and set it up to work with our new sorted array list class. So here in sorted array list demo, I'm going to go down to where we're creating our numbers list. I want to change this so that instead of using list interface, we're going to use sorted list interface. And instead of creating an instance of array list, I'm going to create one of sorted array list. I'll go and use the quick fixes here to go ahead and have Eclipse import the new interface and the new class. And then I'm actually going to go up and take a look at the imports, and I'm going to get rid of the old imports for array list and list interface because they're now unused. So we're going and constructing a new list of this sorted array list type here. When we go and add the values, it'll go and add them in sorted order. So when we go and print things out, everything should be sorted already. Let's go ahead and run this and see what happens. You can see here that, in fact, the values that we get back are sorted. So we're in good shape here. We now have a sorted array-based list implementation, and we earlier did our sorted linked list implementation. For this lecture's participation project, I want you to download the participation project's starter code from eCampus. In there, you'll find a sorted linked list class, and I need you to go and create a new method inside of that class. The method is going to be called reverse sort, and what it needs to do is take whatever is in the list already and go and reverse the order that things are sorted in. So if you start off where the list contains integers and they're sorted so that the lowest numbers come first, after you go and reverse the sort, the lowest number should come last. You're going to have to design things here so that when you go and run reverse sort, it prevents any more items from being added to the list. So you're going to have to figure out a strategy that essentially goes and blocks add from placing anything else in the list after reverse sort has been called. When you turn in this project, just turn in your modified sorted linked list class. That's where we're going to end things for this look at sorted lists. If you have any questions, please join the Q&A session or send me an email. Thanks, and have a great day.